In this video, we're going to present fractals that are generated through the use of random numbers. Random numbers will generate a large number of points, and then these points are transformed by some geometric way. But the problem is that it takes a long time, and so I'm just going to show you a few cases, and most of the time I'm going to be showing you screenshots after I let the program run for a little while. So let's get started. And we're going to start with DUSTB. DUSTB is presented in Lower's book, pages 93 to 97, figures 515, 516, 517. Uses rotation, scaling down, and mirroring of point to produce fractal objects as dust. That means a collection of points. The function that I use is this one, where P is the level of geometric transformation. A, B, C, and D are parameters that are used in these generic geometric transformation equations to produce the points that we use. Again, this is translated from BASIC, and you will references to the sub 140 and so on. So this one takes a lot of time, and so that's what I'm showing you here. It's the figure that gets generated by those points. And so this nice pattern is generated by A equal 0.5, B 0.5, C equal 0.5, D equal to minus 0.5, with 10 levels of fractal generation. Again, this takes a little while. If you use A 0, B 0.7, C 0.7, D 0, then you get this is sort of a could look like a leaf. It's also generated through points, random generated points that are then transformed. But you can tell the self-similarity in these two figures. And so in this one, it starts looking like another leaf, like a tree leaf, with values of A, B equal 0.6, C 0.53, and D equal 0, and 10 levels of fractals. This is another self-similar figure, another fractal dust, produced by A equal 0, B equal 0.771, C 0.5, and D equal minus 0.5. And here's another case where you get these self-similar figures as dust with different values of the parameters A, B, C, and D. When you download this, I have left here for you to try these examples. All you have to do is just copy these, paste it in here. Wait, I need to delete Control V to paste. No, I didn't paste it. Let me go here. Control C. Delete, Control V. There you go. And then you have to put a level here. Again, it depends how much time you want to spend in this. Just to show you here, I'm going to put P equal 3. And you get some points in there. Those are the basic points that generate the first figure. And then at different levels, you're going to start generating more and more points. The problem is that for P equal 10, there are so many points that it taxes the memory in SMath Studio, and it delays the production of the figure. So that's what I just have, those screenshots. Now let's go for the second case, which is simply called dust. And this produces this particular figure that has some self-similarity to it. You can tell. I mean, like this figure is repeated at a smaller scale in here and in here and so on. And this is for using 1,000 points. That take a long time to produce, and the book actually called for like 10,000 points. The next example that's available in here is called a BROWNL line, and this is basically what will generate a random motion, generate a random number here, and then the vertical position of my particle, it's generated based on that random number. In one of the animation videos from a previous video list, you could find the application of random Brownian motion also. Now, Brownian, in this case, we're generating 2,000 points, and because it's just a simple generation, it doesn't take that long. And whenever you recalculate the page, then you get a different Brownian curve, because basically you're generating a new set of random numbers. Okay, so try this one. Is actually relatively simple. Then we have Mira. This is based on a model of coordinates x and y based on a certain function, which is this quadratic fraction function for a equal 1 and fx equal x, page 138, figure 7.5. We are I'm going to do a relatively simple one here, like we're going to put 100 points and see what we get out of it. Apparently for 100 points it doesn't work. For 1,000 points, oh, because it's generating them, so I don't need to worry about that. Let me try 10 just to get something out of it. This is that M has not been defined. Oh yeah, you need to have like 1,000 points or more. I actually tried with 2,000 and I get these. The textbook called for using 12,000 points, so that's going to be like a long hours, perhaps hours in SMath Studio, but it produces a nice figure. But you can still see, you can start seeing the pattern that's going to be generated with this Mira orbit model, which produces a fractal figure, a fractal object. And then we finally have Mandelbrot set. This is taken from a different book, the Talent Course book program, in page 99-100. Paso means step, and n is the number of points that are going to be generated. And so this takes a lot of time, because you go from 1 to Paso, which is 200 times, and then from you keep increasing I equal 1 while I is less than n, so you go 100 times. That's right there, you get 20,000 iterations of this figure. And so it took me a while to produce this. For example, for this case, for 50-50, but here I try 150, and you start seeing that shape that you recognize at Mandelbrot set, although it's pretty gross at this point, but you start getting that famous shape of Mandelbrot's set. And so with the presentation of Mandelbrot's set, the Brownian line, Mira's dust, and these dust cases where you get self-similar figures, and this DUSTB where you get many different self-similar figures. We're going to conclude this particular video and the whole series about fractals in SMath Studio.